Welcome to This Explainer. Today, we're diving into what has to be one of the most fascinating and frankly visually bizarre concepts in all of astrophysics, the eyeball planet. It's one of those ideas that completely pushes the boundaries of our imagination, yet it's totally grounded in cutting-edge planetary science.
Now I know it sounds literally like something out of a sci-fi movie, right? A giant cosmic eyeball just floating out there in the void of space. But today, we're going to look at the latest astronomical research to see why these strange, staring worlds might actually be our absolute best hope for finding extraterrestrial life. It turns out, what looks like a creepy movie prop might just be the most common type of habitable real estate in our entire galaxy. So here's our roadmap for today. First, we'll break down the anatomy of an eyeball planet. Then we'll look at their extreme climates of fire, ice, and snowballs. After that, we'll journey into the Terminator zone. And finally, we'll talk about how we're actually hunting for these exoplanets right now. All right, Section 1, the anatomy of an eyeball. Let's figure out exactly how these bizarre worlds form. So the key player here is a gravitational quirk called tidal locking. Over millions of years, a host star's massive gravity pulls unevenly on a closely orbiting planet, literally creating a physical bulge on the planet's surface. This constant pulling creates gravitational drag. Think of it like a giant brake that gradually slows the planet's spin. Eventually, the planet's rotation perfectly matches its orbit. It's actually exactly how we only ever see one side of our own moon from Earth. These planets lock into place, always showing the exact same face to their sun. One side is baked in a permanent, unending day, while the other is plunged into eternal, freezing night. And the result of this tidal locking is absolutely striking. If a planet has plenty of water and sits at just the right distance from a dim star, the constant radiation intensely heats the dayside. This creates a liquid pupil, a massive active ocean of liquid water right at the substellar point, which is the exact spot where the sun is directly overhead. Meanwhile, the dark side is this eternally frozen shell of solid ice. Put it all together, and you get a planet that looks exactly like a giant eyeball staring unblinkingly at its star. Moving right along to Section 2, fire, ice, and snowballs. Let's dig into the extreme climate dynamics of these locked worlds. Depending on their exact distance from the star, we actually get two distinct flavors of eyeball planets, with some wild temperature swings. You've got your hot eyeballs, which orbit much closer in. Their dayside is so roasting hot that the pupil is essentially a lava world or a barren desert, while the nightside is an icy cap where all the planet's water is trapped in a deep freeze. Cold eyeballs, on the other hand, sit slightly further out. They're mostly frozen shells of ice, kind of like ocean worlds, pierced only by a single, relatively temperate liquid ocean pupil staring right into the star's warmth. But keeping that perfect eyeball state with a liquid ocean sitting right next to an icy shell is a really delicate balancing act. Climate models show this environment is governed by something scientists call the weak temperature gradient. Basically, this is the complex dance between incoming solar energy and how efficiently the planet's atmosphere and oceans move that heat from the hot day side to the freezing night side. Strong winds from the day side can actually push drifting sea ice from the dark side directly into the sun. If too much of that ice melts, it absorbs massive amounts of heat from the water and atmosphere, setting off a devastating chain reaction. Because if the atmosphere is too thin, or if that crucial ocean heat transfer just fails, the entire planet can succumb to a sudden and total global freeze. It goes from this dynamic, potentially habitable eyeball to a lifeless, totally frozen snowball state. Interestingly enough, geological evidence suggests our very own Earth went through similar extreme snowball states billions of years ago before bouncing back. Okay, Section 3, life in the Terminator zone. If the planet survives without freezing over, it creates an incredible sanctuary for life.
UC Irvine's Dr. Anna Lobo actually brings up a huge point here. We always tend to assume that vast water worlds are the absolute jackpot for alien life, right? Well, on a tidally locked planet, a deep global ocean might just evaporate into a runaway greenhouse effect on the permanent day side or freeze completely solid on the night side. Instead, water-limited planets with plenty of exposed landmass might actually be the most climatically stable environments for life. The land provides friction, and that prevents those runaway atmospheric effects and stabilizes the whole climate.
Imagine just taking a walk across this sweet spot. Scientists call it the Terminator zone, the exact boundary line separating permanent day and permanent night. First, you'd start at the scalding hot coast, a dry savanna getting blasted by hot winds and intense UV radiation, where maybe only extreme, heat-resistant microbes could survive. Then you'd step into the twilight sea, a vast, ring-shaped ocean, existing in a state of permanent sunset. Aquatic life here might actually evolve to absorb infrared light from their dim star. Finally, you'd hit the freezing, jagged glacial edges of the cold coast, watered by the melting ice sheets of the dark side. It's just a wild, narrow ribbon of habitability.
Living in this perpetual twilight wouldn't exactly be a peaceful, romantic sunset on the beach, though. You would be dealing with incredibly intense weather. Because superheated air is rapidly rising at the sun-facing pupil, freezing cold air rushes in along the surface from the frozen dark side to replace it. What that means for you is perpetual tropical storms and relentless gale force winds. It acts like a planetary conveyor belt, constantly transferring heat across the surface just to keep the atmosphere somewhat balanced.
Which brings us to our final section, the hunt for exoplanets. Let's see how astronomers are searching deep space for these worlds.
Get this, an astonishing 70% of all stars in the universe are red dwarfs. 7-0. These stars are much smaller, dimmer, and cooler than our own sun. Because they're so dim, their habitable zones, the exact area where liquid water can exist, are pulled extremely close to the star. And being that close almost guarantees the planet is going to experience the tidal locking we talked about earlier. So eyeball planets aren't just some rare, weird anomaly. They are likely the statistical norm for habitable planets across the cosmos.
And we are already finding amazing real-world candidates out there. Take a planet like LHS 1140b, where the data strongly suggests it could be a cold eyeball with a liquid pupil right now. Or Wolf 1069b, an Earth mass rock sitting perfectly in its habitable zone. And of course, the incredibly famous TRAPPIST-1 system, hosting 7 roughly Earth-sized planets packed closely together, several of which are tidally locked right in the habitable zone. These aren't just math equations on a chalkboard. These are actual mapped addresses in our galaxy, where conditions are just right.
So how do we actually check them for life? Well, since they orbit so incredibly close to their dim stars, they cross in front of them, or transit, really frequently from our point of view on Earth. That frequent transiting allows powerful tools like the James Webb Space Telescope to capture starlight as it filters directly through the planet's terminator atmosphere. By looking at how that light breaks apart, we can scan for chemical biosignatures. Basically, we're looking for atmospheric imbalances, weird combinations of methane, oxygen, and carbon dioxide that just shouldn't coexist in large amounts unless a biological ecosystem is down there actively producing them.
I want to leave you with this final, provocative thought. When we look up at the stars, we aren't just out there looking for another Earth. We are looking for entirely new, completely alien ecosystems. If life did manage to take hold in the turbulent, eternal twilight of an eyeball planet, how weird and wonderful could it be? Imagine evolving under a sun that never sets, driven by eternal storms, and living beneath a sky that never fully darkens. It's a lot to think about. Thank you so much for joining me on this explainer, and keep looking up.